So now that we have all the equations we need for our bubble and dew point calculations, we can go ahead and code these into Python and get those numbers. So I'm going to start with the bubble pressure calculation, and I'm going to do this by creating its own function to calculate the bubble pressure. So for this calculation, we need to pass the moles of our mixture, the mole fractions of our mixture, and the temperature that we're at. So I'm going to go ahead and add a line of code called x, and that will be our distribution of benzene and toluene. So the mole fractions for benzene and toluene. So the mole fraction for benzene is 0.3 and the mole fraction for toluene is 0.7. And then right above here, I'm also going to create our CHE tools object that gets the properties for benzene and toluene. And we'll use these properties in actually all of our calculations. So they'll be extremely useful in our code. So for our bubble point calculation, or our bubble pressure calculation, the bubble pressure is when the sum of the vapor pressures, or the bubble pressure is just the sum of the vapor pressures at that temperature. So all we need to do is return the sum of those vapor pressures. So it'll be the sum of our mole fraction of each component times the saturated vapor pressure, the pure component saturation vapor pressure of each component at that temperature. And so now we can go ahead and test out our function. I will pass it x, which is the moles of benzene and toluene, and I'll also pass a temperature. I'm going to go ahead and do 50 degrees Celsius, which is 323 degrees Kelvin, and that is our bubble pressure. So now that we have that, we can go ahead and create another function that will calculate our bubble temperature. So say for the same thing, we need to pass our mole fractions for each mixture, or for our mixture, and then we also need to pass it pressure, because this calculation is done at a constant pressure. And now, if you remember from the first video, we need to use a root solver to solve for the temperature. So I'm going to go ahead and create another function inside here, which I'll just call equations, that we use for our root solver. So since we're using it for the root solver, we're going to pass the values, the unknowns to it as a vector, and in this case our unknown is just temperature. So I'm going to unpack that. So for our bubble temperature calculation, we want to raise the temperature until the bubble point of the mixture is equal to our desired pressure. So to do this, we just need this expression to be equal to 0. So we're going to reuse our bubble pressure function. And so when this expression is equal to 0, then we'll be at the bubble temperature. So we just need to return this from our function that we're going to use in root solver, and then we just need to solve it using root. So we'll pass it our function, and then we'll also pass it a guess. Since we're guessing temperature, I'm going to guess around 300 Kelvin. I need to make sure that this is being returned as an array, since root solver expects it that way. And then we need to return this down here. So now I'm going to go ahead and test out our bubble temperature calculation. Again, we need to pass our mole fractions, and then for the pressure, I'm going to use the bubble pressure from our previous calculation. And if this is done correctly, then the bubble temperature should be equal to 323 kelvins. And it is. So the bubble temperature at this pressure is 323. I'm just going to go back up here and grab the first element of the x attribute. So that way, this function just returns the integer value. So now that we have our functions to calculate the dew point and bubble points for a mixed solution, we can now generate the liquid vapor equilibrium phase diagram for this mixture. So I'm going to start by creating a variable that will be our x-axis, and that will be the mole fraction of our least volatile compound. It's always graphed on the x-axis. This is just a common practice in chemical engineering. So to do this, I'm just going to create a linearly spaced array going from 0 to 1, and I'm going to put in 11 points. That way, we're using 11 just because if you look at Z1, it'll be a nice even distribution from 0 to 1. And so then from our first component, we can use those mole fractions to calculate the mole fractions of our second component, which I'll call Z2, and that'll just be 1 minus Z1. So now if we print Z1 and Z2, this would be the mole fractions of benzene, and this would be the mole fractions of toluene. I'm also going to define our temperature, which is 120 Celsius or 393 Kelvin, and our pressure, which is 150,000 pascals. And these are the constant temperatures and pressures we'll be using to generate our graphs. So now I'm just going to set up the graph and get it ready to start adding in our points. It'll kind of make it easier later on once we graph our y, or once we calculate the y values, just to kind of put them in this graph. So I'll do figure 1.make subplots, and I'm going to set the rows equal to 1, and the columns will be equal to 2. We'll have 2 rows, or 1 row and 2 columns in this. So from here, we can now go ahead, and I'm going to start with our dew pressure and bubble pressure calculations, because we'll be plotting those on the same axes. So for our bubble pressure, I'm just going to call it bub P for when we graph. All we need to do is calculate it using our function here, but we don't even need to use the function since it is a very linear calculation. I'm just going to type in the values to make it easier. So it's just the sum of the mole fraction times the pure component saturation vapor pressure. So coming back down here, it will be our mole fraction times the pure component vapor pressure, so the mole fraction of benzene, times the pure component vapor pressure of benzene. And so to get this, I'm going to index into our p.pvap to get the first value, which is just the number for benzene, and then it will be our moles of toluene, or our mole fraction of toluene, times the pure component saturation vapor pressure of toluene. So we'll index in and get the first value. So now if I go ahead and print this out, it gives us the bubble pressures. I should be using Z1 and Z2, that's why I wasn't giving. So now this should give an array of our values. So these are the y values that we'll use in our graph. So let's come down here and we'll add scatter. Our x value is just going to be Z1, which will be the moles of benzene, our most volatile component. The y value is going to be the bubble pressures that we calculated. And then this graph will be in row 1 and column 1. And so there is our bubble pressure curve. And since the dew pressure is calculated in a similar way, I'm just going to calculate it in one line like we did with the bubble pressure without our function. And in this case, it is just our mole fraction 1 over the sum of our mole fractions times the components, pure component saturation vapor pressure. So it will be 1 divided by the mole fraction of benzene times the pure component vapor, or pure component saturation vapor pressure of benzene, plus the mole fraction of toluene times the saturation vapor pressure of toluene. And I can go ahead and graph this the same way I did our bubble pressure. So I was getting an error in my code where the dew pressure line was graphing as a flat curve. I found the issue. Instead of the mole fraction divided by the pure component saturated vapor pressure, I was multiplying them together. So now if we divide them, there is our dew pressure curve. So now we need to do this same thing, but for dew pressure and dew temperature, or dew bubble temperature and bubble temperature and dew temperature. But since these aren't linear calculations, we're going to have to do them a little bit differently. And how I'm going to do this is by creating a for loop to calculate the bubble temperature for each pair of our mole fractions. So I'm going to start by creating a for loop. So for each value of x1 in z1, x2 is going to be 1 minus x1, which we have up here. And then I'm going to create an array so that we can combine these two together. And we'll be able to pass it to our functions to create, or to make that bubble temperature calculation. So I'm going to set x equal to the number array, and it's just going to be x1 comma x2. And now we can use this to calculate our bubble temperature. So our bubble temperature will just be equal to our bubble temperature calculation for x and then our constant pressure. So since we're running this through a for loop, instead of just assigning the value at the end, because that would only leave the last value in our bubble T variable, I'm going to create a list, and then we are going to append each of these values to the list. So every time we run through the for loop, it's going to make a calculation and then add it to this list. So if we print it out at the end, this should give us all of the temperature values that we're going to graph for our bubble temperature calculation. So I'm going to come down here and create another scatter. Our x variable is still going to be z1. This time I'm going to use the bubble temperature variable I created, and we're going to be graphing this in our second column. So there is the bubble temperature curve at a constant pressure of 150,000. And now that's all left to do is do the dew temperature calculations. So I can actually do these very similar to our bubble temperature calculation. I just need to change some of the variable names and the function that we're using. So I'm going to call this dt instead. Since it is vapor mole fractions instead of liquid mole fractions, it's no longer x values, they are y values. So I'm going to change everything from y1 to y2. And then we're going to be appending our dew temperature values to this list using the dew temperature calculation we created earlier. And so then I just have to add this to the graph. And go ahead and graph it. And there are our dew and bubble pressure curves and our dew and bubble temperature curves.